Hello viewers, I am Vikshmaya Chalakani, Assistant Professor of Physics from Government Degree College for Women, Nalgonda. In this lecture, I am going to explain reversible and irreversible process and the work and heat concepts and the zeroth law of thermodynamics and the work in free expansion of gas. Okay, we see the zeroth law of thermodynamics. So this law gives the concept of temperature. Whenever the two bodies are in thermal contact, so one physical property of the system remains constant as time progresses. So that constant which is that physical quantity which is constant is called temperature. So we say that those two objects are in thermal equilibrium. Okay. So here the concept of thermal equilibrium is explained in case of three objects. Okay. So according this law, when a body A is in thermal equilibrium with a body B and also B in thermal equilibrium with a body C separately, then the two bodies B and C will be in thermal equilibrium with each other. So it is the zeroth law of thermodynamics. When a body when a body A is in thermal equilibrium with body B and also with C separately, then B and C will be in thermal equilibrium with each other. So it is the zeroth law of thermodynamics. So it is very clear. So we are defining the thermal equilibrium for the two bodies independently. A is in thermal equilibrium with B one time and A is in thermal equilibrium with C in other case. So then B and C will be in thermal equilibrium. That means, so we can say B and C possess the same temperature. We are not keeping B and C in contact. Without keeping B and C in contact, we are saying that they are in thermal equilibrium. That is the key point here. Okay, generally, when do we say the two objects are in thermal equilibrium? So if we keep them in contact with each other, uh, so we keep them in thermal contact. So the contact should be thermally conductive. So therefore here we are not keeping B and C in thermal contact, but whenever they are separately thermal equilibrium with the third body, so the two bodies will be in thermal equilibrium. It is the zeroth law of thermodynamics. So the name zero is given for this law and it is invented after the laws of first law of thermodynamics and second law of thermodynamics. So this is the primary concept. So as compared to those laws, therefore, so it is put before 1. Generally in our numericals, so we start with 0, 1, 2, 3 and 9. So just like that. So 0 is treated as earlier than 1, therefore it is called as zeroth law of thermodynamics. So this is the basis of temperature measurement. So this concept is the basis for temperature measurement. A closed system and its surroundings can interact in two ways. So system and surrounding, here it is closed system, can interact in two ways. So the two ways are, one is by work transfer. System and surrounding can interact by work transfer, and the second way by heat transfer. So these two processes, work transfer or heat transfer, are called as energy interactions. energy interactions. So now reversible process. A process which can be stopped at any stage and can be reversed so that the system and surroundings are in exactly restored to their initial states. Okay, such process is called a reversible process. So any process we can stop at any stage and we can uh, trace back the situation. So if they attain the same similar properties, so those properties are represented with the state of the system. Therefore, we are saying if we trace back the situation, if the system and surrounding both attain the earlier states, so in that case, we say that the process is reversible. So the characteristics of above process, reversible process, it, it must pass through the same states on the reversed path. So if we reverse the path, so they should attain the same states. That means they should attain same properties. So it must pass through a continuous series of equilibrium states. And whenever the process is occurred, it is the succession of states. So, or we can say continuous states, but those continuous states should be equilibrium, a series of equilibrium states when we are traversing in reverse direction. No real process is truly reversible in reality or in practical. No process is no process is reversible, but some process may approach reversibility to close approximation. That means by taking some approximations, some process some processes are reversible process. So examples for reversible process are given here. The expansion and compression of a spring. So within the elastic limit, we can add one word within the elastic limit. So however we expand the spring, if we release the force and it goes to the earlier situation. So that is one example. So isothermal expansion or compression. So this process also example for reversible process, and another electrolysis and frictionless adiabatic expansion or compression of a fluid. So these are the examples. So another one. So if we cannot, whenever we reverse the process, if we cannot get the initial states, so our system or surroundings do not get the initial states, such process are called irreversible process. So here it should be written irreversible process. So these are the examples. Now, so these are the examples for irreversible process. First one, relative motion with friction. Whenever there is friction, there are some heat losses, and whenever we trace back the process, or if we do the process in reverse direction, the heat losses do not come back. Okay, they are exhausted or dissipated. So we cannot get the dissipated energies. So therefore it is irreversible. So combustion also. If we burn the matter, we get energy and some ash or dust. So if we keep the dust together, we cannot form the earlier matter. So diffusion also. So mass transfer occurs, some explosions we can say. So in such case also, uh, we that is irreversible process, and diffusion also, and free expansion of gas also example for irreversible. Throttling electricity flow. In case of electricity flow, there is heat loss through resistor. So heat transfer. It is easy to transfer heat from hot body to cold body. So, but we can reverse the situation. We cannot reverse the situation. So irreversible, and plastic deformation also. So just before I said the stretching of spring, that is within the elastic limit. If the elastic limit is crossed, we say that is plastic deformation. Okay, uh, they, the object will not come back to the initial position. So this process, that means irreversible process, is represented by a dashed curve to indicate that the intermediate states are indeterminate. So indeterminate. So generally the reversible process is represented with a solid line, and irreversible process is represented with a dashed curve. That was solid curve and it is dashed curve. By the gaps between the dashed lines indicates those intermediate states are indeterminate. So here it is shown in diagram. So we show the reversible process. That means there is state change. So initially it was in first state. After the process, it attained second other state. So we represent with solid line. So irreversible process is represented with dashed curve or line. So now here work, work and heat are two quantities. Work is a transient quantity which only appears at the boundary while a change of state is taking place within a system. So work may be done within a system or outside the system also. If the work is done inside the system or within the system, that work is called internal work. If the work is done outside the system, that means the work may be done on the system or work may be done by the system. So in that case, we call it as external work. External work. Okay. Therefore, the first half of the definition is corresponding to internal work, and the second definition, the second part of the definition is corresponding to the external work. So, in case of external work, work is a transient quantity which only appears at the boundary, while a change of state due to the movement of a part of the boundary under the action of force. So if there is movement of the part of the boundary or maybe the whole boundary also. So whenever there is a movement of part of the boundary or whole boundary, so the physical quantity which appears across the boundary, that one is called work. Okay. So this boundary movement is because of the action of your force. The boundary movement is because of the action of your force. So such one is called external work. If the work is done by the system, there is sign convention in calculating. Whenever we use these quantities in mathematics, so the sign convention is important. Therefore, here the sign convention is stated according this. If the work is done on the system, sorry, if the work is done by the system on the surroundings, then the work is said to be positive. So it is represented with plus W, plus W. So the example for positive work, the fluid expands, the fluid in a cylinder expands by expelling, that means by pushing the piston outward. So in fluid expansion, volume increases, so the piston is re- pushed by the fluid. Therefore, the fluid is pushing the piston. So the gas is doing the work, or the system is doing work. So in that case, we take it as positive. So simply we say that the work is done by the system on the surroundings. So that is positive work. If the work is done on the system by the surroundings, the work is said to be negative. Okay, we take it as minus W. So the example for negative work, the compression of fluid by a force on piston. So in above case, volume increases. In this case, compression of fluid, the volume decreases. So it is possible when there is a force on piston. That means the force from external side. Okay. So it is the example for negative work. So work is a path function. So in the last class we have studied what are point functions and what are path functions. So work is a path function and it is not a physical uh, property. So it is a quantity, so exists during transition. So therefore these are inexact differentials. So we write whenever there is state change from state 1 to 2. So the work done is shown with this notation. Okay, it is equal to W12. So but not equal to W2 minus W1 we have seen in the last class. So we represent this notation with these symbols. So and another quantity, similar quantity is heat. So it is defined as a quantity. We can say heat is a quantity or heat is something which appears at the boundary when a system changes its state due to a difference in temperature between the system and its surroundings. So whenever there is a temperature difference between system and surrounding, one physical quantity appears across the boundary. That means one physical quantity transfer occurs. That physical quantity is heat. So if the heat flows from the surrounding to a system, the quantity is said to be positive. It is a sign convention in case of heat. So if the heat flows from the surroundings to system, that means heat received by the system, we can say. So in that case, we take the heat as positive. That means plus Q. So if the heat flows from the system to the surroundings, it is said to be negative. Or we can say heat rejected by the system or heat given up by the system, and we take it as minus Q, minus Q, and we represent this state change or the heat involved with this notation. Okay, one more thing we have to remember. So dV is point function, that means volume is point function and work is dW. So the small work is path function. So dV is point function and dW is path function. It is 1 by P. So we call this 1 by P as some integrating factor. an integrating factor. So whenever we multiply the inexact differential with an integrating factor, that inexact differential converts into exact differential. Okay, so it is one we can see from this equation. So however we get dw is equal to pdv. From that equation, dv is equal to 1 by p times dw, and if we observe this equation on RHS side, so it is inexact differential and it is exact differential. Of course, p is there. P is also exact differential quantity, but it is in denominator. So we can get the conclusion that whenever we multiply inexact differential with an integrating factor, that converts into exact differential. Right. Similarities between heat and work. So these are the two quantities we have seen now. So what are the similarities and dissimilarities between these two quantities? Heat and work are the forms of energy in transition. Whenever the transition is occurring, so at that time only, so these two quantities involved, so they are forms of energy. So but the condition, they are not possessed by the systems. So the heat is not possessed by the system, or work is not possessed by the system in equilibrium state. But whenever there is state change occurring, and whenever there is no equilibrium, in that case, so these come into the picture. So both are path functions and inexact differentials. Okay. Both are boundary phenomena. So these are occur at boundaries only. So both are associated with a process, not a state. So it is, these quantities are associated with a process, but not, these quantities do not exist in a state of the system, stable state of the system. The systems possess energy, but not work or heat. We have discussed this. So if we see the dissimilarities, heat transfer when T heat transfer when there is temperature difference. Okay, so heat transfer occurs when there is temperature difference between system and surrounding. So another point, so if the system is stable and there is no work transfer between system and surrounding. So if the system is stable or equilibrium, there is no work transfer between system and surrounding. But so here there is no work transfer, but there may be heat transfer. But there is no restriction on heat transfer. It is a dissimilarity between work and heat.